Have you ever wished you had an extra pair of hands around the house? Someone or something that could just handle the tedious stuff, load the dishwasher perfectly every time, tidy up without being asked. Well, what if I told you that future isn't decades away? What if it's starting to take shape right now in labs and maybe sooner than you think in homes? Forget the clunky, slow-moving robots of old movie tropes. We're talking about machines designed to move like us, learn like us, and maybe, just maybe, help us live better lives. But how close are we really? Let's unpack what's happening because the ground is shifting fast. We're witnessing a surge, a genuine acceleration in robotics, particularly in humanoids, robots built in our image. It's moving beyond flashy, controlled demonstrations into something far more significant: the development of machines capable of navigating and interacting with our world, the messy, unpredictable human world. Two companies are making serious waves right now, showcasing distinct but equally compelling visions for this future. Westwood Robotics with their athletic Themis V2 and 1X with their home-focused Neo. These aren't just competing products. They represent different philosophies on how to build and train the next generation of robotic helpers. So, grab a metaphorical seat, because we're going on a deep dive into what makes these bots tick and why it matters way more than you might initially think. Let's start with Westwood Robotics and their impressive Themis V2. Picture this: a robot standing about 5'3" tall. For many of us, that's practically looking at IT. It's not some towering industrial behemoth, nor a small tabletop gadget. It's designed on a human scale. And that scale is important because it suggests interaction, working alongside us, using our tools, navigating our spaces. One of the standout features they're touting is its 40 degrees of freedom DOF. Now, degrees of freedom sounds technical, but think of it like this. Imagine all the ways you can move. Your shoulder can rotate, lift, swing. Your elbow bends, your wrist twists and tilts, your fingers curl and splay. Each independent way a joint can move counts as a degree of freedom. 40 DOF is a lot for a robot. It signifies incredible flexibility and potential for complex movement. The arms alone have 6 DOF each, similar to a human arm's range, allowing them to reach around obstacles or position themselves precisely. But then, the hands, or end effectors as engineers call them, add another 7 degrees of freedom each. That's huge. Think about the dexterity needed to pick up an egg without crushing it, turn a key, or maybe even use a screwdriver. That level of fine motor control in the hands is what separates a clumsy machine from something genuinely useful for intricate tasks. This is Themis V2, the second generation. That detail is crucial. It tells us Westwood isn't starting from scratch. They've built a V1, learned from its limitations, identified weaknesses, and iterated. Engineering, especially in robotics, is all about this cycle: build, test, fail, learn, improve, repeat. They specifically mention upgrading the arms for better articulation. This isn't just about waving hello. It's about giving the robot the fluidity needed for tasks requiring real dexterity. Imagine trying to thread a needle or carefully place a component onto a circuit board. That's the kind of refined movement improved articulation enables. It's the difference between swinging a hammer and performing delicate surgery. Now let's peek under the hood, metaphorically speaking. Themis V2 uses something called Actuators, which stands for Backdrivable Electromechanical Actuator for Robotics. Okay, let's break down Backdrivable. Imagine pushing a heavy door that has a very stiff, jerky hydraulic closer. You feel resistance. It might slam. It doesn't move smoothly with you. Now imagine pushing a perfectly balanced old door. It glides effortlessly in either direction. Backdrivability in a robot joint is closer to the second scenario. It means the joint can be moved smoothly and easily from the outside without fighting against a rigid internal mechanism. Why does this matter? Lifelike movement. It eliminates that jerky, mechanical clunkiness you often see in older robots. The movements become more fluid, more organic, more, well, human-like. Safety, this is paramount, especially for robots intended to operate near people. If a backdrivable robot arm accidentally bumps into you, it's less likely to feel like a rigid metal bar hitting you. Because the joint can give slightly under external force, it can sense resistance much more effectively. Think of it like gently nudging someone versus bumping them with a locked elbow. The robot can feel the contact, understand it's met an obstacle like a person, and react accordingly, perhaps stopping or adjusting its path. It makes interaction inherently safer and less intimidating. It's about control and awareness, not just brute force. Powering the brain of this machine is some serious computing muscle, around 200 tops, or tera operations per second. Forget trying to visualize a trillion operations. Just know that this is a massive amount of processing power packed directly into the robot. Think about how quickly your own brain processes information when you walk across an uneven lawn, catch a ball thrown slightly off target, or navigate a crowded room. You're constantly taking in sensory data, making micro-adjustments, predicting outcomes. Themis V2 needs this kind of horsepower to run sophisticated artificial intelligence, AI, and machine learning, ML algorithms on board. This means it doesn't need to constantly send data to a remote server and wait for instructions. It can perceive its environment, analyze the situation, and react in real time, making it far more responsive and autonomous. Imagine it needing to quickly sidestep an unexpected object. That onboard processing makes the difference between a smooth dodge and a clumsy collision. And how does it stay upright and aware of its own motion, especially when things get tricky? Enter the 3DM-CB7 AHRS sensor from MicroStrain by HBK. AHRS stands for Attitude and Heading Reference System. The source material perfectly nails the analogy. It's like an inner ear on steroids. Your inner ear helps you sense balance, acceleration, and orientation. This sensor does the same for the robot, but with incredible precision and speed, updating up to 1,000 times every second. Imagine knowing exactly how you're tilted or turning, 1,000 times in the blink of an eye. This constant stream of high-fidelity orientation data allows the robot's control systems to make instantaneous adjustments. This is critical for handling uneven surfaces, walking upstairs, recovering from a stumble, or executing quick turns without toppling over. It's the foundation of dynamic stability. All this hardware needs sophisticated software to orchestrate it. That's where the Robot Operating System, ROS, comes in. ROS is a flexible framework, a set of tools and libraries that developers use to write robot software. Think of it less like Windows or Mac OS and more like a standardized toolkit for robotics. It allows Westwood's engineers and potentially future developers to program complex behaviors, integrate new sensors, teach the robot new skills, and tailor its responses for specific scenario without reinventing the wheel every time. So what can this athletic robot actually do? Westwood claims it can walk at a typical human pace and impressively run up to 10 kilometers per hour, about 6.2 mph. That's a respectable jogging speed. If you decided to go for a run in the park, Themis V2 could theoretically keep up. They're even hinting at more dynamic capabilities, showing it running and suggesting it might be capable of parkour-like maneuvers or jumping over small obstacles. The key takeaway here isn't just the speed. It's the implication of dynamic stability and real-world capability. They are explicitly designing this machine to handle the unpredictability of the real world, rough terrain, sudden pivots, obstacles. If Themis V2 can remain stable and functional when the floor isn't perfectly flat, or when it needs to react quickly, that represents a significant leap beyond robots confined to the pristine conditions of a lab. This robot looks poised for anything from demanding industrial tasks, requiring dexterity and mobility, to potentially even assisting in more dynamic, unpredictable environments. Westwood's Themis V2 presents a compelling vision of a highly capable, physically adept humanoid robot ready to tackle challenging environments. But what if the biggest challenge isn't running fast or navigating rough terrain, but mastering the chaotic, endlessly varied and deeply personal space of your home? That's where our second player, 1X, comes in with their robot, Neo. While Themis V2 seems built for performance, 1X's Neo is being explicitly aimed at the domestic sphere. The vice president of AI at 1X hasn't been shy, posting videos online showcasing Neo engaged in tasks that might seem mundane at first glance. Picking up fallen leaves in a yard, loading items into a dishwasher, and even tidying cushions on a sofa. Now your first reaction might be, picking up leaves, big deal. But hold that thought. The real significance lies in the word autonomy. 1X emphasizes that Neo is performing these tasks on its own. There isn't someone off camera with a joystick meticulously controlling every movement. Neo is using its sensors to perceive the environment, its AI to make decisions in real time, and its motors to execute the task based on that understanding. Seeing a robot autonomously spot scattered leaves, figure out how to scoop them up, navigate to a bag, and deposit them, that's a complex chain of perception, planning, and action. It's easy to fake robotic capability with remote operation, often called telepresence or Wizard of Ozing. True autonomy, where the robot decides and acts independently, is infinitely harder and far more meaningful. Let's look at the dishwasher demo. The video shows Neo picking up a cup, transferring it deftly from one hand to the other, a surprisingly complex maneuver requiring coordination and grip adjustment. Aligning it with an open slot in the dishwasher rack and placing it inside. Again, it might not look like a Hollywood blockbuster scene, but think about the intricate calculations involved. Object recognition, identifying the object as a cup. Grasping, applying the right amount of force, not too tight to crush, not too loose to drop. Adjusting for the potentially slippery surface. Manipulation, the hand-to-hand transfer shows advanced coordination. Spatial awareness, understanding the 3D space of the dishwasher rack, the orientation needed for the cup to fit. Path planning, moving its arm and the cup without hitting the sides of the dishwasher or other items. Balance, maintaining its own stability while bending, reaching, and carrying an object. Yes, the demo conditions were simplified. The dishwasher was already open, the cup conveniently placed, but it serves as a perfect illustration of the foundational steps required to tackle the controlled chaos of a typical home. It's about mastering these seemingly simple building blocks of domestic chores. Then there's the cushion scenario. Neo walks over to a couch, identifies a cushion, picks it up and places it down neatly. What's interesting here is watching it maintain balance while leaning forward, holding a soft, somewhat unwieldy object. Cushions aren't rigid. They deform, their center of gravity can be awkward. Anyone who's tried to neatly arrange decorative pillows knows they don't always cooperate. Watching Neo manage this highlights the constant balancing act required for humanoid robots performing physical tasks, especially those involving interaction with non-rigid items. It requires subtle, continuous adjustments, much like we humans make unconsciously. The 1X team is quite open about why they're focusing on these seemingly simple domestic examples. They illustrate the complexity of real-life tasks. Homes are the opposite of structured, predictable factory floors. They are inherently messy and dynamic. You have carpets and rugs with varying textures, furniture that gets moved, unpredictable lighting conditions, pets wandering underfoot, kids leaving toys scattered around. A robot designed for the home has to be able to handle this constant variability. It can't just freeze or fail when something unexpected happens. According to 1X's AI lead, Everything shown in their demos is driven by data and a comprehensive neural network that controls the entire robot lower body, spine, arms in a coordinated fashion. They're using techniques like reinforcement learning, RL, particularly for the lower body's dynamic movements, and integrating it seamlessly with the control of the upper body. RL is a type of machine learning where the AI learns by trial and error, receiving rewards for successful actions and penalties for unsuccessful ones, gradually figuring out the best strategy to achieve a goal. Here's where their strategy gets really interesting, drawing parallels to how Tesla approaches self-driving AI. One X believes that tackling the highly unstructured environment of the home, what they call the final boss of robotics, is paradoxically the fastest way to develop truly capable, general-purpose intelligence. Think about it. If you train a robot only in a perfectly organized warehouse where every shelf is labeled and every path is clear, the robot gets very good at being in that specific warehouse. It might struggle dramatically when faced with a slightly different, messier environment. The argument is that these structured environments, while seemingly easier to start with, don't provide enough diverse data, enough weird corner cases, to truly push the AI's learning and adaptability. A home, on the other hand, is an unstructured data goldmine. One minute, the robot might be folding laundry, dealing with soft, deformable objects. The next, it might need to navigate around the family dog who has decided to nap in the middle of the kitchen floor. Then, it might try to open a jar of pasta sauce, realize the lid is stuck tight, and need to figure out how to apply more torque or perhaps even ask for help. Each of these small, everyday scenarios presents unique challenges and generates invaluable training data. This constant exposure to novelty and unpredictability forces the AI to become more robust, more adaptable, more generally intelligent. It's like learning to cook. You can meticulously follow recipes in a perfect kitchen, structured environment, or you can learn by trying to make dinner with whatever random ingredients you have left in the fridge, adapting and improvising as you go unstructured environment. The second approach, while messier and involving more potential failures, arguably leads to a deeper, more flexible understanding of cooking. 1X is realistic. They admit Neo isn't ready to flawlessly transition from loading the dishwasher to doing a full load of laundry and then mopping the floors. It's not there yet, but the core philosophy is to let the robot try, learn from its mistakes, and continuously improve through exposure to the real world's messiness. It's the same principle behind how large language models improve, by processing vast amounts of diverse text data, including all its quirks and inconsistencies. Structured environments, like perfectly smooth highways for self-driving cars, don't provide enough challenging scenarios to foster rapid growth. The chaos of city driving, or in Neo's case, the chaos of a home, is actually the key ingredient for accelerating learning. So here we stand, looking at two compelling approaches. Westwood's Themis V2, a powerhouse of hardware, sensors, and onboard computation, seemingly built for high performance and adaptability in potentially demanding physical environments. And 1X's Neo, focused intently on the home, using the very unpredictability of domestic life as a crucible to forge a general-purpose AI through relentless data collection and learning by doing. Both represent significant strides towards the long-held dream of capable, autonomous humanoid robots. It's crucial to remember that it's still early days. Neither of these robots is about to replace human workers wholesale or become a standard home appliance tomorrow. There are immense challenges still to overcome in areas like battery life, cost, safety certification, robustness, and the sheer breadth of skills needed for true general-purpose utility. However, the pace of progress is undeniable. The advancements in actuator technology, sensor fusion, AI processing power, and learning algorithms are converging. These aren't just theoretical improvements. They are manifesting in machines that can run, balance, manipulate objects, and start performing tasks autonomously in ways that seemed firmly in the realm of science fiction just a few years ago. We are watching the transition from specialized, single-task robots, like robotic arms in factories or vacuum cleaners, towards machines with the potential for much broader applicability. The future these developments hint at is one where robots might assist the elderly, perform dangerous jobs, handle logistics and delivery, manage household chores, and perhaps even become companions. What does all this rapid advancement teach us? Perhaps the most important lesson is about adaptation and the nature of learning. Both Westwood and 1X, in their own ways, are building machines designed to adapt Themis V2 to physical challenges, Neo to environmental chaos. And Neo's approach, in particular, highlights a fascinating idea: that true intelligence, true capability, might not arise from carefully controlled perfection, but from resilience forged through navigating messiness and learning from countless imperfect attempts. Maybe there's a lesson there for us humans too. Embracing challenges and learning from our stumbles is often the fastest path to growth. My advice: stay curious, keep an open mind. This technology is evolving incredibly quickly, and it will impact our lives. Understanding the progress, the challenges, and the different approaches being taken is crucial for navigating the changes to come. It's easy to react with either utopian excitement or dystopian fear, but the reality will likely be far more nuanced, complex, and interesting. It's a wild time to be alive, watching this future unfold. Thank you so much for joining me on this exploration today. I hope you found it as fascinating as I do. Wishing you all the best of health and happiness. If you enjoyed this deep dive and want to stay updated on the mind-bending world of emerging tech, robotics, and AI, please consider hitting that subscribe button. It really helps the channel out and ensures you won't miss the next video. Thanks for watching, and I'll see you in the next one.